Dear everybody, first of all, let me thank the organizers for giving me the opportunity to present this video poster today at the Cortona video conference. Today I would like to present some of the recent work I did in collaboration with Igor Pesando at the University of Torino, and specifically I will talk about fermions on the strip in the presence of boundary defects and their interpretation as a conformal field theory in the presence of excited spin fields. Before diving into the subject, let me just quickly recall a few properties and why spin fields are relevant for what we do. Spin fields are a set of fields which appear in conformal field theories, meaning that they are specified by a conformal weight and their application points. Their short-range behavior with fermions is what gives the good boundary conditions that we need to include fermions in the theory. That said, it means that they are extremely relevant for any computation involving fermions in these theories. For example, and to give you some motivation behind the study of spin fields, suppose that you want to compute some phenomenological amplitudes in string theory, and for example, you want a particle physics related phenomenological model in string theory. You will need these kind of fields. This is because, for example, in the computation of Yukawa couplings in string theory, and extremely related to that in any computation involving orbifolds or d-branes intersecting at an angle, you can find this kind of fields localized, for example, at the intersections of the brane, where also chiral fermions can appear. We are therefore interested in being able to compute correlation functions involving any number of spin fields, as well as any number of spin fields and any number of matter fields. This is because they might appear in phenomenological amplitudes in string theory. And how to do that? Well, at least in the abelian case, which means spin fields which do not mix together families of fermions, we already have two very well-established approaches. The first one, also in chronological order, is the region vertex, a very old approach, and the bosonization procedure, which up to today is the state of the art. We do not intend to replace them completely, but we may be interested in going back to the problem and try to find a more direct way to compute these amplitudes. This is because we may be interested in extending the procedure to abelian twist field correlators, as well as to non-abelian twist and spin field correlators, for which there is no established procedures up to date. In doing that, we may get some insight also in the question on why there is no bosonization equivalent procedure for twist fields. As a bonus, we might also gain access to applying this kind of procedure to other fields, such as, or to other scenarios, such as the replica trick and the computation of the entanglement entropy. The way we tackle this is by considering a certain amount of families of complex fermions defined on the string worldsheet, where we have a time direction going from -infinity to +infinity and another direction going from 0 to pi. We then introduce n different point-like boundary defects at sigma equals 0. These defects are in correspondence to changes of coordinates for one of the endpoints of the string. Namely, the string doesn't change its boundary conditions until it reaches one of the defects and then proceeds with the new boundary conditions. This actually introduces in the theory a time dependence given by the point-like defects. And this brings to the question, is this still a CFT? Well, this is object to a proof later on. And from now on, what I can show you doesn't rely on conformal field theory properties, but this is all field theory properties. We then move to the complex plane, where we keep considering the same amount of complex fermions defined on C, and where the change of coordinates that we had on the strip have become monodromy properties of the fields. And the presence of point-like defects has translated into the presence of branch cuts onto the Riemann surface. We can therefore afford to study the theory on such a Riemann surface in the presence of the cuts and to completely absorb the monodromy properties inside the definitions of the modes. This leads to an algebra of the operators completely time independent and to a non-perturbative approach to the problem, meaning that I'm not including one defect at a time, but I'm actually considering them all together at the same time. I can now show you what I meant before, and let me consider just one family of complex fermions. The definition of the modes of these fermions defined on the complex plane in the presence of the branch cuts completely encapsulates the properties of the monodromy, showing the change of coordinates given by the point-like defects on the boundary of the strip originally defined. The particular behavior of the modes and the properties of the algebra of these kind of fermions are exactly what gives a non-conventional behavior of the fermions on the vacuum of the theory. In particular, we might start to suspect that something is definitely happening given by the boundary defect. In fact, we might be even more specific and think that something is there to provide this kind of non-conventional short-range behavior between the fermion and the vacuum of the theory. The explanation for what's happening may be given by taking a look at the stress energy tensor of the theory, which is non-conventional for a fermion defined on the strip, and that shows both first-order and second-order singularities in the position of the defects on the complex plane. This kind of singularities have a very precise interpretation, and this is probably the first time where we can find a stress energy tensor of this kind with this kind of properties. This stress energy tensor is peculiar in its own way. Specifically, the boundary defects have already introduced a time dependence inside the theory, which we saw earlier, and the stress energy tensor is showing plenty of that in its singularities. However, even though it is time dependent, it is coming from a conformal field theory, since, and you might have to trust me on that, its canonical OPEs are perfectly okay. And this is quite a remarkable result in which a time-dependent stress tensor comes from a still conformal field theory. From the second-order singularities, we learn that there are indeed spin fields creating the vacuum. And from the first-order singularities, we also learn that spin fields are interacting among them. We can also have the weights of the spin fields, which completely characterized the fields, and as promised, we can also compute the correlators of spin fields, actually in the excited spin fields. This is because we have complete control on the operator algebra of the theory, which is what allowed us to discover the spin fields in the first place. It's what allowed us to compute properly the stress energy tensor and show that the time dependence nonetheless leads to a conformal field theory. This means that we can also compute correlation functions involving matter fields, because again, we completely have control of the algebra of the theory. We therefore have an alternative way of computing this kind of objects, alternative to the region framework and to the bosonization procedure. This way, though, is a bit more direct, and we hope to be able to extend it to the cases I showed you before with success. I would then like to thank you for the attention and remind you that I'm completely available for discussions and exchange of ideas.